All right, thank you. Yeah, I gave a similar talk here in August, if you were here, but this time there will be some overlap, but I will try to make it more general and like throw all my open problems at you, hoping that something will happen. The main theme of this talk would be that Boolean function that has simple Fourier transform also have small complexity. Can you see this red? Whatever. And obviously there are various ways to interpret this statement, right? You can measure the complexity of the Fourier transform of the function in several ways, and you can also think of many different computational models by which you measure the complexity of a function. So we'll get to it. We'll define whatever needs to be defined. I should also mention that there are many results also in the other direction, where you choose function with small complexity and you show properties of the Fourier spectrum, like low degree concentration or stuff like that. But I'm going to talk about taking function that the Fourier transform behaves in a special way, not what you would expect from a random function, and then see what we can say about its complexity. So let's just figure out what we're going to do. So the first type of functions I will speak about is function with small spectral norm, which I will define, and what can you say about the circuit complexity and the decision tree model. And the second type of functions, those are Boolean functions who have very few non-zero Fourier coefficients, which will also relate to communication complexity and decision trees. So everything will be defined, so hopefully it will be okay. So just to get my notation clear, so we're looking at the vector space of function from this group Z2 to the n into the real numbers, and then you have the Fourier characters. The chi alpha of x is just -1 to the inner product with alpha and x, and you write every function as a linear combination of those functions. This is all standard. And obviously, we're interested in Boolean functions, that is, functions that only takes the values plus and -1. So it's a bit natural to figure out that obviously not every linear combination of those functions would give you a Boolean function, and it has to be a rather special linear combination for the function to take only the values plus and -1. I mean, not just any linear combination you would pick up off the street would do it. You have to be, some structure must be there if you want the function to be Boolean. So let's define the spectral norm, or the L1 norm of such a function, of a Boolean function, which is just the sum and absolute value of the Fourier coefficients. For example, the L2 norm is always 1, right? That's the Parseval's theorem, and the L1 norm can be large. It can be as high as 2 to the n over 2, and for some function, that's the number. And of a random function, if we just for every vector in Z2 to the n, you just flip a coin and decide 1 or -1, then it's going to be large, something exponential in n. So the question is, when is it small? I mean, what does it mean for a Boolean function to have a small spectral norm? Here's a nice collection of such functions, which are indicators of subspaces, of Z2 to the n, or subgroups. So if f is an indicator function, or a characteristic function of such a subspace, then the spectral norm is bounded by a constant, which happens to be 3. But again, by an indicator function, I mean that it is -1 is the true value of a Boolean function. So it is obviously it doesn't matter. So it is -1 inside the subspace and 1 everywhere else. So its spectral norm is at most 3. And there are, so just a few examples, that the end function is that's not the common way you would think about the end function, but it's just indicator of 1 point. So it's a shift of the zero subspace, and the OR function and the XOR function are all such functions, and for all such functions, again, the L1 norm is at most 3. Now, obviously, if you take a linear combination of such a short linear combination of such function, you would also get function with small spectral norm, and it turns out to be essentially the only case. So here's a theorem by Green and Sanders, which says that suppose f is some Boolean function with L1 norm bounded by m. M is just some real number. Then you can write this function as sum of plus and minus 1 of indicators of affine subspaces or cross sets, and L is bounded by this 2 to the 2 to the O of m to the 4th. So as scary as it might seem, it doesn't depend on n, right? It only depends on m. So the only way you can construct a family of function with constant spectral norm is by taking a linear combination of constantly many indicators. So you may notice this already gives you something computational about such functions. So let's define this complexity class. AC0 with 2 is the class of Boolean function which can be computed by circuits with polynomial number of gates. The depth is constant, and you have unbounded fan-in and or not and parity gates. Those are your building blocks, the usual and or and not, and you also have mod 2 gate. So by this result of Green and Sanders, you already get that if m is O of 1, function with constant spectral norm are in fact in AC0 with mod 2 gates, which is kind of nice because we know we can do without the mod 2 gates, right? We know XOR of n variables is not in AC0, and its spectral norm is 1. But once we add those mod 2 gates, those parity gates, we get all function of constant spectral norm for free. So I'll just go briefly how we do it. So every indicator of subspace is just and of some linear equations. So it is in AC0 with mod 2 gates. You just take the basis for the perpendicular subspace, and you check that all the equations in it are satisfied. So maybe you need to add some NOT gates. So once you have this, you just need to sum all the subspaces, right? But there are constantly many of them. So just you take the majority, you check whether there are more than 1 or minus 1 or whatever. But the important part is that the number of bits in this computation is just constant. So no matter how you do it, you get this circuit with a number of gates, which is, again, we said m is constant, so it's some constant times poly n, and the depth is also like constant. Constant depends on how do you implement this part, but it's constant. So so that's the first example. We said we take function with small spectral norm, we get something about this circuit complexity. So let's move on to talk about this. Oh, this, yeah.
There are better bounds, right, on the Green Sanders.
Are there?
Or no?
I don't know.
I thought there were.
Does anybody?
Four Chinese papers. I thought that.
Oh no, it doesn't. It doesn't.
Better bounds on this.
No, they don't get very better bounds.
It's specific with communication.
Yeah, so that's. But anyway, you don't know, Fanny.
Yeah, but I thought that their paper doesn't give any, as far as I know.
That's good. Quick question.
Yeah.
Don't you lose another exponential by having to compute majority in constant depth?
But the majority is over this constantly many bits.
Yes, but that constant is 2 to the 2 to the m to the 4.
Oh, you mean this? So I didn't carefully analyze this.
But what do you mean you lose?
So it might be a larger constant. That's what you mean.
It's 2 to the 2.
Right. But yeah, but it's still a constant. So
They're not disjoint, the subspace? They're not disjoint, the affine subspace?
no, they don't have to be.
It's not really a sum.
Hmm?
There's a sum of the indicator function.
Right.
Is it really the sum of the indicator functions? I mean, then if it's an integer sum, then they're disjoint, and then you can do this in lots of ways.
No, but there's plus and minus 1. They can be.
Ah, okay.
They can be cancellations.
Sorry.
All right, so let's talk about decision trees. So this is like a definition by a picture of what the decision tree is. It's just a tree. On each internal node, you query a variable. If it's 0, you go to the left subtree. If it's 1, you go to the right subtree. And then on the leaves, you have the values of the function. So this is a decision tree for a majority of 3 bits. You can just check. And obviously, every function has such a tree. And it's like probably the most simple computational model you can think about. But we're interested in a generalization of a decision tree, which is a parity decision tree. So now we're allowing every internal node to query a linear function of the inputs. You just query chi alpha of x for some alpha. And if it's 1, you branch this way. And if it's -1, you branch that way or whatever. So this can be much stronger. Like the XOR function, you would always need to query all of your bits. Whereby if you're allowing yourself to make linear queries, you just need 1 query to compute the XOR of n bits. So it can be stronger. So here's just some notations. The D with this parity of f is just the minimal depth decision tree which computes f, and size with parity of f, that's minimal size of a parity decision tree, where we measure size by just the number of leaves in the tree. So it's not hard to figure out that if a function is computed by a parity decision tree with size s, then the L1 norm is at most s.
So the size is depth or number of bits?
No, size is number of leaves, yeah. So the way you do it is you just write your function as a sum of indicators over the leaves of the tree, and each such indicator, that's a 0, 1 indicator. So it has spectral norm 1, and you just use triangle inequality, and you get s. And they can be quite far apart. So for the AND function, we said that the L1 norm is at most 3, but the size of the decision tree is at least n, and you can do like n, where the decision tree for n, for example, is depth n, but the size is also n, because you have this a very unbalanced graph, right, for unbalanced tree. So that's also the case for parity decision tree. You must have at least n queries, so the size also need to be omega of n. But so you can't really expect. So we're looking at like a characterization of can you compute a function with small spectral numbers by small decision trees? So you can't. So this gives you some limits to what you can expect. But n is still pretty small, right? This can be 2 to the n in the general case. So here's what we do know, that if the L1 norm is at most m, then the size is this n to the m squared. So again, if m is constant, then the size is polynomial, whereas generally it can be exponential. And the way to prove this theorem is this lemma, which says that for any Boolean function with L1 norm m, you can find a hyperplane, just a restriction of f. So if you restrict f to this hyperplane, the spectral norm drops by something significant. So I'm going to state what I want to say more precisely. So here's the lemma. If the spectral norm is m, and you have your 2 largest coefficient we denote by alpha and beta, and f chi alpha plus beta equals z is just a restriction to this hyperplane, then if you restrict to chi alpha plus beta equals 1, then the spectral norm drops by m minus f out of alpha, which is at most m minus 1 over m. And if you restrict to -1, then it drops by the second largest coefficient. Or it may be that the roles of 1 and -1 are reversed. So I have it by a picture. So this is like a decision tree, parity decision tree picture of this lemma. You begin with a function with L1 norm m, and you, if you follow this path, you have a function with L1 norm m minus 1 over m. And here, so I didn't care to write all the details, just what we need. So here you have a function with specular norm at most m. So let's just give the proof. So what we wanted to prove is this theorem. So now the proof is just by induction of m. So you look at the worst case of n variable function with L1 norm m, and the key the lemma just stated tells you that if you query at the root of your tree the chi alpha plus beta, with alpha plus beta being the two largest coefficients, then you get on one side a function on n minus 1 variables with L1 norm m minus 1 over m, and on this side a function with on n minus 1 variables with L1 norm m. So you just get this inequality, and you solve it, and that's what you get. And if you're being a little more careful, or if you also consider the loss which is on this side by the second largest coefficient, then you can even do a little bit better. This 2 to the m squared n to the m, but it would still be nice to say something much better, like to give something polynomial both in n and in m, or to say something meaningful also in the case where m is polynomial in n, or to show that you can't. We don't know. So this is the decision tree, the parity decision tree construction, which also gives you a formula. So what's the formula? I'm just going to define it for those unfamiliar with the lingo. So a formula is just a circuit with every gate having out degree 1. So just an example, you have this Boolean function, and how does the formula for it might look? So you take the end of x1 and x2, and now we end with x3. And here you take the end of x1 and x2, and the not of x4. And the point here that you can't use the fact that you computed x1 and x2 over here in order to save up the calculation over here. You must redo the calculation because you have this property that every node has out degree 1. So yeah, so that's a formula for a Boolean function, which can be larger than a circuit, obviously. Yeah, so we're denoting by L of f is just the minimal size of the Morgan formula, which computes f. So what the Morgan formula is a formula where your gates are fan in 2 of and or and not. For example, the XOR function can be computed by a formula of O of n squared. So just like for free, when you have a decision tree, you get also a formula of not too large a size, right? If the parity decision tree is S, if the parity decision tree size is S, then the formula size at most S times n squared. So remember, we had a bound on this for a function with small specular norm. We want to bound this. So this is just a short observation where you do an induction on S, right? You have this on the root, you have chi gamma, and a function f left and f right. This is a linear function, an XOR of at most n bits. So its formula size is known to be, this is in fact tight. This is theta of n squared. So if you write f this way, this chi gamma and fl, or not chi gamma and fr, you get, again, this recursive inequality, which you just solve. So what you get is that function with small specular norm not only have small circuits, but also small formulas, small De Morgan formulas. So again, this is the bound on the size of the decision tree, and this is what you get when you transfer to a formula. And formulas, which is, so you can also balance formula, right? You can always make the depth theta the log of the size of the formula, so you also get a bound on the depth of the formula. So obviously, you can also think, so the previous construction using the Green and Sanders theorem, you can also consider what happens there when you construct a formula. And then the question is, like, what values of m are you interested in? If m is constant, then over there you have better bounds, but the moment f becomes non-constant, then this might be a little better. And again, we would like to say something meaningful when m is polynomial in n. So in this case, both constructions are completely useless. It would be nice to say something. Or again, to show that you can't say anything. All right. So that concludes what I had to say about function with small L1 norm. Let's move on to talk about sparse Boolean functions. So the sparsity of a function f. Oh, yeah, question.
What about approximating such functions by?
Yeah, so for approximation, we do know that that if f has, again, L1 norm m, you can epsilon approximate f by parity decision tree with depth O of m squared plus log 1 over epsilon. No n. But yeah, but we don't know anything about tightness of this theorem. But yeah, and by epsilon approximation, I mean that it's a Boolean. The parity decision tree computes a Boolean function, and it agrees with f and at most but epsilon fraction of the inputs. That's the notion of approximation. All right, so now I'm done with function with small specular norm, and let's move on to talk about a sparse Boolean function. So again, sparsity is just the number of non-zero Fourier coefficient. Here's a notation. This f hat with 0. And again, just a random function would have almost all of them non-zero. So you expect a sparse function to be special in several ways. And again, if f is computed by a parity decision tree with depth d and size s, then the sparsity is at most s times 2 to the d, which is at most 4 to the d. And this is again the same proof by writing your function as the sum of indicators of the leaves of the tree. So here's an example of a sparse function. It's called the address function. So your input is just log n bits, x1 and 2x log n, and then another n bits, y1 to yn. And your output is the y variable, which is indexed by the x variable. Right? This gives you an index between 1 to n, and the value of the function is just the y variable, whose address appears in this box. So this is a function over n plus log n variables, and its sparsity is n squared, which is very small compared to 2 to the n. And it's also quite easy to see that this function is computed by a small decision tree. Right? You need to query the bits, the x bits, and then there's only another relevant variable, the y bit that you need to query, and then you know the value of the function. So this leads to this conjecture that there is some constant c with every Boolean function f. The parity decision tree depth of f is at most log sparsity to this constant c. So let me try to give some motivation for this conjecture. Well, one motivation is that like we all know like 10 Boolean functions, right? And all of them, for all of them, it's true. So, you know. But another motivation comes from communication complexity. So I'm just going to quickly go over what is communication complexity. So you have a function f from 0, 1 to the n cross 0, 1 to the n to 0, 1, a Boolean function. You have Alice on one side with x, Bob with the other side on y, and you want to compute f of x and y. So they talk to each other, right? I mean, unless f is really simple, they must talk to compute this function. And the deterministic communication complexity of f is just the minimal number of bits they need to communicate in order to compute f. So I'm only considering now deterministic protocols. They're not allowed to flip coins. They must be always correct. And this is the communication complexity of f. So just observe that if you have a parity decision tree for f with depth d, then that gives you a protocol with 2 times d bits, right? Because on every node, you have this linear function on your variables. There's just a sum modulo 2 of the x variables and a sum modulo 2 of the y variables. So Alice computes her sum, Bob computes his sum. They just exchange the outcomes. They determine this sum, and they just move along the tree. Right? They speak to each other. So that begins to show why is this even relevant. So now, for every function f, you construct this matrix mf with this 2 to the n times 2 to the n, and every entry of mf indexed by x and y is just capital F of x and y. And then it is well known ever since before I was born that the communication complexity of f is at least the logarithm of the rank of mf, and it is conjectured that it is polylogarithmic in the rank of mf, and that is called the log rank conjecture. It's a major open problem. But now assume your function is of this very special type. F of x and y is just this lowercase f evaluated at x XOR y for some Boolean function. So yeah, those are called XOR functions. So we're not again in the general setting where you're allowed any function from 0, 1 to the n cross 0, 1 to the n. We're just looking at XOR functions. And now if you construct this matrix MF, then the eigenvector is just the Fourier characters, and the eigenvalues would be the Fourier coefficients. So the rank of MF is just the sparsity of f, of little f. So again, this is I won't do the calculation, but this is just one line to be convinced that's the case. So if this conjecture, which I started with, is true, if the parity decision tree depth of f is polylogarithmic in the Fourier sparsity, then you would prove that the log rank conjecture holds for the special case of XOR functions, right? Because we saw that given a parity decision tree, you get a protocol, and this protocol cost would be polylog in the sparsity, which is polylog in the rank of capital F. So that's, I mean, obviously that's not an if and only if. I mean, it can be that you could find other protocols for XOR function which are not based on parity decision trees, but that's perhaps one way to prove it. So I would just comment that the best separation we know between those two quantities is a function f whose parity decision tree is at least the logarithm of the sparsity to the 1.63. So this polylog cannot be, it can be like with c equals 1, right? There must be some separation. So this is the same function you construct, for those of you who know this, to separate the log rank from the communication complexity, deterministic communication complexity, and you get here log 6 to the base 3, which is 1.63. Again, this is a very nice construction of a Boolean function. I won't get into the details because I don't have much time, but that's what it gives you. So let's figure out how would we prove this theorem. I mean, what happens to the Fourier transform of f when you restrict to this hyperplane? So now you look at your subspace modulo alpha, right? You have, before restriction, you have all the F Fourier coefficient, and now you look modulo alpha, right? So every such two coefficient, like f hat of beta 1 and f hat of beta 1 plus alpha, they would just collapse to the single coefficient f hat of beta 1 plus f hat of beta 1 plus alpha, and so on for every pair which equals modulo alpha. So obviously what we would like to show, we want the sparsity to drop, we would want to find such alpha which will have many pairs collapsing to the same coefficient, many pairs in the support. Now obviously, for example, if I could find one that always cuts the support by half, then that would be great. But I know I can't because of the separation we just said. So so we want to find such alpha which would collapse many together, but we don't know how many we can even hope for. But let's consider the special case where F has both small spectral norm and both sparsity, small sparsity. That's like I'm being very greedy in my demands. But now we know that the parity decision tree depth of F is at most m squared times log s. So again, if m is constant or even logarithmic in F, that's this conjecture is true. And I'm just going to, so I think that's the paper, Avi, you was mentioning by Tsang, Wang, Shi, and Zhang. So they show independently that you can even take it to be m log s. So let's show the proof. It's not hard. So remember this key lemma I had that says we can find a hyperplane which reduces the spectral norm to be m minus 1 over m. So if we just apply it, m squared times, we get an Fn subspace with codimension at most m squared, where f is constant, right? Because it can't go below 1. So I'm starting with m and just keep scraping off this 1 over m of the spectral norm. And after at most m squared restriction, I'm going to get to a constant function. So just there are m squared linear function that you can fix them in a way that f is now constant. That's the theorem. So now let's think about this tree. I'm just on the ith level. I'm querying chi alpha I, where these are those special linear function. So I know there exists one path on which the function is constant, right? That's the theorem. So let's try to think what would happen on any other path of this tree. So now what I claim is that since here the function is constant, then in fact every non-zero coefficient had to cancel out, right, with another coefficient. Otherwise, the function would have a non-constant Fourier coefficient, and it would not be constant. But the fact that they cancel out specifically means that they collapsed again to the same coefficient. So it doesn't matter which way, which values I restrict chi alpha i's. It only matters which function I restrict, right? So because if you restrict, exists some values beta I that if you restrict f to those values, you get a constant function. So for every non-zero f hat of beta, there must exist some non-zero f hat of beta plus gamma, with gamma in this span of these vectors, for them to cancel out, right? Because again, you look at your space modulo alpha 1 to alpha m squared. So that's exactly what we wanted, right? We said we want to, so f hat beta and f hat beta plus gamma would collapse to the same coefficient, so you would cut the support by at least 2, right? For any values beta prime I, you would select the sparsity. The Fourier sparsity is at most half of what you begin with. Let's go back to the diagram maybe. Right, so here I know I'm constant, but here I know that the worst thing that can happen is that I have a function with half the sparsity. So I made some progress, right? And after at most log s steps, we get a constant function in all leaves. So in fact, so So what was important about the argument was finding this large subspace, right? I didn't care what it is, but so you can fact that the same proof shows that if you want to prove that the parity decision tree depth is polylogarithmic in the sparsity of f, it's enough to prove this conjecture that for every Boolean function f, there's a subspace with codimension polylog of the sparsity on which f is constant. Because then you would do the exact same proof, right? And you get a higher exponent, but still something polylogarithmic in S. So, so I just want to that, I mean, obviously this implies this, right? Because this tells you that on all paths you have a constant function. This one just requires to find one path. So, so those are in fact the equivalent conjecture, and again, we don't know what's how to prove it. So so let's just summarize what we had. So about function with small spectral norm, we know many things. We know again they have small circuits, small formula, small parity decision tree, and I didn't show it, but it's also true that they also have small randomized communication complexity, and then by result of Gavinsky and Lovett, they also have small deterministic communication complexity. So the log rank conjecture, which we talked about, is true for function with constant spectral norm. And sparse functions are much more mysterious than those types of functions. So we mainly have, or I mainly have open problems and not much progress over there. So, so that's it.
Are there any questions for that?
Yeah.
A couple of years ago, Montanaro and Osborne had a notion of quantum Boolean functions. Do you know if any of these properties make sense in that setting?
No, I don't know what I went on.
Okay.
Yeah.
So roughly how does the proof of that theorem on the right go?
Yeah. So what?
How does the proof of that theorem on the right go?
Oh, so it's exactly the same trick, this main lemma trick, that you, again, on every node, you just query chi alpha plus beta, where f of alpha and f alpha plus and f hat beta are the two largest coefficients. And you do this recursively. And then you just observe that if you stop after this number of levels, and you have this, so on every, after this number of levels, you may have a leaf with a function which is not constant, right? Some sub-function, some restriction of f. But you just round every such leaf to like the majority, or if it's balanced, just pick whatever. And then you show that that's an epsilon approximation for f.
Any other questions? No? Okay, let's thank Ben again.